Welcome back to Boson Buzz. I'm Monty Molecule. Today we're talking about two things that seem utterly different, a whisper and a hurricane. One is gentle, the other is devastatingly powerful, but they are both, at their heart, the same thing, a flow of air. For most of human history, we've treated moving air and water as forces to be fought. We build thick hulls to push through waves and powerful engines to muscle through the sky. But what if fighting is the wrong approach? What if, instead of battling the flow, we could persuade it? What if we could whisper to the water and ask it nicely to let our ships pass? That's the art and science of the fluid dynamicist, and they are teaching our biggest machines to fly on a cushion of cleverness. Think about the last time you put your hand out of a car window. If you held it flat, the air pushed it back hard. That's drag. If you tilted it slightly, it might even lift. That simple experience is a tiny lesson in fluid dynamics, the study of how liquids and gases move. For engineers, fluid dynamics has always been the enemy of efficiency. It's the invisible hand that slows down cars, planes, and ships, forcing them to burn more fuel to push against a relentless, chaotic flow. The traditional solution has been more power, more thrust, more brute force. But look at nature's champions of movement. A shark isn't a brute force swimmer. Its skin is covered in tiny tooth-like scales called denticles that subtly channel water over its body, reducing drag and even creating tiny vortices that give it extra thrust. A kingfisher bird dives into water at high speed with barely a splash, its beak perfectly shaped to slice through the interface between air and water with minimal resistance. These creatures aren't fighting the flow, they are masters of collaboration. They have spent millions of years evolving shapes and surfaces that communicate with the fluid around them. Scientists and engineers have taken note. The new goal isn't to overpower the chaos, but to calm it. The first major battlefield for this new philosophy is one of the biggest polluters on the planet, the global shipping industry. A massive container ship longer than 3 football fields burns hundreds of tons of the dirtiest fuel just to push against the water. An enormous amount of that energy is wasted on two types of drag. Skin friction, which is the water clinging to and scraping along the hull, and pressure drag, which is the ship's blunt shape creating a huge turbulent wake that literally sucks it backwards. It's like trying to run through a swimming pool while wearing a giant billowing coat. The fluid dynamicist's answer to skin friction is a concept called the air-lubricated cavity. It sounds complex, but the idea is elegantly simple. What if you could separate the ship's hull from the water itself? Engineers have developed a system that releases a fine curtain of millions of microscopic air bubbles from slots along the front of the ship's flat bottom. These bubbles don't just float away, they expand and stabilize, forming a persistent, frothy layer between the steel hull and the ocean. This bubbly layer is a game changer. Water mixed with air is much less dense and has far less friction than water alone. The ship essentially slides over this bubbly cushion. It's not flying, but it's as close as a 200,000-ton metal box can get. Trials have shown this single innovation can reduce the drag on the ship's bottom by a staggering 20 to 30%. That's like taking 1 out of every 4 engines on the ship and just turning it off, saving a fortune in fuel and slashing emissions. But the fluid dynamicist isn't done. While the bubble skirt handles the bottom, the sides of the hull still suffer from skin friction. This is where biomimicry, copying nature, comes in. Inspired by the fast, silent swim of sharks, researchers have developed riblet films. These are vinyl sheets covered in millions of microscopic grooves, all aligned in the direction of flow. To the naked eye, it looks smooth. But to the water flowing over it, these tiny grooves prevent cross currents from forming, keeping the flow attached and orderly. It's like giving the water tiny rails to follow, discouraging the chaotic swirls that cause drag. Applied to an airplane or a ship, it's like putting the vessel in a slippery second skin. The most advanced systems, however, are active. They don't just have a static, clever shape like a shark's skin. They have a kind of intelligent, living skin. Imagine a flexible, high-tech film, like a giant, super strong sticker, applied to the entire hull of a ship or the wing of an airplane. This film is embedded with a grid of thousands of tiny sensors, each thinner than a human hair. These sensors aren't cameras. They are pressure pads and flow detectors. They constantly listen and feel the water or air flowing over them in real time. Their job is to detect the birth of turbulence. Turbulence doesn't start as a giant wave. It starts as a tiny, microscopic swirl, a rebellious eddy trying to break away from the smooth, orderly flow along the surface. In the old world of brute force, that tiny swirl would grow, gather friends, and become a chaotic, energy-stealing mess. But in the world of active flow control, the sensor that feels that tiny swirl sends an instant message to an even tinier neighbor, a microscopic actuator. These actuators are the real marvel. They might be tiny holes that can open and close, or little hairs that can vibrate, or membranes that can pulse. When they get the signal, they respond with pinpoint precision. If a tiny swirl is trying to spin clockwise, the actuator right next to it might release a microjet of water or air spinning counterclockwise, canceling it out. It's like having millions of microscopic peacekeepers on the surface, whose only job is to gently persuade the flow to stay calm and orderly. They don't fight the entire ocean. They just give a tiny corrective nudge at the exact right place and the exact right time. This creates a real-time, whispering conversation between the machine and the medium it moves through. The hull says, "I feel the first whisper of chaos here," at coordinate X. The active skin whispers back, "I hear you," applying a drop of calm, and smooths it over. This conversation happens millions of times per second, across the entire surface. The result is that the layer of fluid right next to the hull, the boundary layer, stays in a smooth, streamlined state called laminar flow for much longer than nature would normally allow. It's the difference between sliding your hand over a still pond, smooth, laminar, and stirring it with a spoon, chaotic, turbulent. The active skin is constantly persuading the pond to stay still. The results of combining these technologies are not subtle. A ship equipped with a bubble skirt, riblet films, and active flow control can see total fuel savings of 20% or more. On a single voyage across the Pacific, that can mean thousands of tons of fuel not burned and thousands of tons of carbon dioxide not emitted. But the benefits go beyond fuel. By smoothing the flow and reducing the violent buffeting of water against steel, these technologies drastically reduce wear and tear on the ship's structure. The vessel lasts longer, needs less maintenance, and operates in near silence compared to its shuddering, inefficient predecessors. The principles of gentle persuasion are now flowing into other fields. The same concepts are being applied to aircraft wings, where tiny jets of air can prevent dangerous stalls and allow for lighter, more efficient designs. They're in wind turbines, where smart blades can extract more energy from gentle breezes. They're even being tested in water pipelines, where keeping the flow smooth means massive pumps can use far less electricity. This is the core of the new fluid dynamics. It's a shift from an adversarial relationship with nature to a collaborative one. We are learning the grammar of flow, the language of whispers that can calm a storm of wasteful friction around our machines. It proves that the most efficient path forward isn't always to build a bigger hammer. Sometimes it's to learn a more persuasive argument. From a roaring battle against the waves to a quiet conversation with the current. That's the elegant turn we're taking. By learning to listen to the fluid world and respond with intelligence instead of force, we're not just saving fuel, we're redesigning our relationship with the very medium we move through. It's a lesson in humility and cleverness that's making our future cleaner, quieter, and infinitely more graceful. If you appreciate seeing how a little clever thinking can tame a giant problem, please help Boson Buzz keep the ideas flowing. Hit that like button and subscribe for more. Until next time, have a safe and curious week.